Hello and welcome to this session on information retrieval. Today we'll discuss web crawling. If you look at web as a collection of documents, a component such as a crawler which can go and grab the content on the web is of importance to many players. Here are some examples. So we have these content aggregators, we have web archives, we have web monitoring services, and there are many applications which might be interested in the information on the web. And for example, let's say analytics on how let's say how GitHub is doing these days. So that's something that I do as part of my research. And then we have search engines for whom, of course, the content to be indexed comes from the web. Okay. Um, let's take a look at the content aggregators. So content aggregators basically go to multiple sources and fetch related content and then provide them in a nicely presented manner to the users. So for example, let's say Yahoo Finance is a content aggregator which aggregates finance related content. It pulls contents related to finance from various sources. So let's say Bloomberg, let's say Reuters, and so on for news. There might be blogs getting aggregated and so on. And similarly, Rotten Tomatoes, for instance, aggregates reviews for movies, TV series, and so on. So we have many such content aggregators. Usually, these content aggregators work in either pull mode or a push mode. So what I mean to say here is the content aggregator may pull the content from the sources whenever they need it. So for example, let's say there is a news publisher who keeps on publishing news regularly every hour, but the content aggregator may decide to pull the news from that provider, let's say once a day or twice a day. So that's one example of the pull mode. And on the other hand, we might also have a push mode where there could be a tie-up between the source and the aggregator, where the source keeps on pushing the content as and when the content is available, and the data just gets into the content aggregator's repository whenever whenever the source makes it available. So we have both push and pull modes over here. So there are different feed formats such as the RSS feed and so on, which are available here, which enables these push and pull modes. Okay, let's move on to another interesting stakeholder for web crawling, which is web archives. Why would you like to archive the entire web? So here is an example, archive.org, which claims to have 20 plus years of web history accessible through their Wayback Machine, and they claim to have 330 billion web pages, 20 million books, 4.5 million audio recordings, 4 million videos, and so on. What to do with these archives? Well, first of all, just having access to sites which do not exist now could be a wealth of information when it comes to understanding how things evolved in the past. So in a way, they act like a museum. They may also act like a library where you might be able to access books and texts which are currently out of print. And there are also other interesting applications of such an archive. For instance, Cloudflare partners with the Internet Archive to ensure that their distribution of web pages is reliable. So for instance, if the web host is down and there's a request for that web page, they go and access the Internet Archive and take the latest version of that web page and show it to the user. Uh, so there are many such interesting applications of having Internet archives. Archive.org is not the only one who is doing this. We also have a Common Crawl, for instance, commoncrawl.org. Here, they also say that their open repository is available for anyone who is interested in crawl data over a period of time. We also have web monitoring services. Let's say you host a website and you want to know the uptime of your website. You want to know whether the host provides 99.99% uptime as they promise. So how do you check? So keep crawling once in a while and check whether the website is up or not. So this is provided as a service to you by many monitoring services. For instance, we have Statuscake, Montastic, SolarWinds, Pingdom, and so on. So there are many of them who do this. So crawling is an essential service which is not only of interest to a search engine, but since our interest for this course is search engine, we'll now look at crawling from a search engine's perspective. Okay, now when a search engine wants to crawl a web page, what information would the crawler like to know about that web page? So here are some information that I have listed. Firstly, does the site owner allow you to go fetch the page and index it and distribute it? Just because a page is available in the open on the web doesn't mean that it is free and you could download and distribute or republish that information elsewhere. So you might be getting into license issues in that case. So you have to be very careful and you should ensure that the site owner allows you to do this. The way we do this is through a protocol where the site owner mentions the pages that he allows a search engine to crawl and index. We'll get to that in a minute. And we also want to know when the page was last updated. So if we know this, if our previous crawl was within that time limit, then we don't want to fetch this page once again, and that saves valuable time for us. Are there more related pages on the website? So that's another very useful bit of information, because then I don't have to look for URLs in the past content of an existing page and then go ahead and fetch those URLs, which is usually how a crawler works. So now I have some way where I can just go and get the important or related pages quickly. And then we also want to know how important is this page. There could be thousands of pages on a website from a site owner, and not all pages are probably equally important, in which case knowing the importance of the page allows us to get the more important ones earlier than the lesser ones. And finally, we also are interested in knowing how frequently the web pages get updated, so we can tell the crawler to come back again at a specific time uh, uh, to to refresh its index for this web page. But how do we get all this information for an existing web page? There are many ways to get this information: through the sitemap.xml, through the robot.txt, through the header of the file, and so on. We'll quickly take a look at these means. Here is a simple sitemaps file which usually every web host puts on his website. So I pulled this from the ICICI Bank's website. So if you look at this, so you simply go to icicibank.com/sitemaps.xml. So they usually put this file in their root so that the search engines know. This clearly says what is the change frequency of this page and what is the priority of this page. So according to ICICI Bank owners, it looks like these pages are more important than the landing page. And for instance, they have the fixed deposit page, the I wish page, the recurring deposits page, which are priorities of 0.9, whereas the home page has a priority of 0.1. And they also mention the change frequency, so you can expect all these pages to change almost every day, so you want to index them ideally every day. It's prerogative of the search engine whether to really come back and download a fresh content every day, but at least it knows that if it has already fetched it today, then it doesn't have to fetch it once again. Okay, there are many tools to check the header of a web page. You could simply do a telnet or a netcat kind of a thing. So here we do a similar thing through an online interface. This is from websniffer.cc. You might just go hit this URL websniffer.cc and then provide some URL as input and hit the submit button. You could select the kind of request that you want to do, the head request or the get request, and so on. So if you do a head request, then this is what you see, which if you notice tells you that the last modified date of this page is 15th August 2020. It's pretty old, right? So if your crawler hasn't yet has crawled this site later than 15th August, then you don't have to get this page once again. So what's the difference between head and get requests? If you select the get here instead and submit, you would see the HTML content of the page as well. Let's move on. We also have the robots.txt file. Usually this is also placed on the root of the uh, website. So let's say iccibank.com/robots.txt should let you see this file. And on this file, they mention the user agents, which are the crawlers, the name. So every crawler is supposed to have an ID, and this string is that ID. And if you want some rules to be applied to all the crawlers, then you simply put a star over there. And after that, you could say that certain structures within your site are not supposed to be uh, fetched and stored by the search engine. So no search engine is allowed to go to something.com slash your site slash temp folder in this case. So that's what this disallow rule mentions. And here is an example. So for example, the name of the search engine could be search engine, and you could have several disallows under everything. So if you don't have anything disallowed, then it basically means that the search engine is free to crawl anything that is available. All right, so let's see if we can take a quick look at the. Okay, let's start with the sitemap. Sitemaps. So here we have an example sitemap.xml, as I had showed you on the slides. So it's useful to look at the sitemap first before we do the crawling. And you could also check out the robots.txt file. Just see how many pages are being disallowed. This being a banking site, they are probably careful that they don't want all their pages to be searched and indexed. So there's a quite a lot on the disallow list. And interestingly, you can also see how many bots exist. So there's Omni Explorer, Free Find, Become Bot, Nutch, JetBot, WAC, Stanford, Neighbor, and so on. So if you write your own bot, and if ICICI Bank thinks that it should not allow your bot to download their site, they would simply add your bot here and disallow everything there. So this slash basically means disallow everything. Um, all right. So these pages are disallowed for all search engines. All search engines. Yeah. So that's about the robot.txt. We have seen the sitemaps as well. So here is the robots database. This is not maintained anymore, as they say, as they claim, but you will be surprised that there are so many bots. Many of these bots, crawlers are also called as bots or spiders or robots. So these crawlers usually belong to some search engine or the other, um, and in some cases they may belong to some third-party apps, the monitoring services, and so on, as we discussed, the content aggregators and other apps, as we just discussed. Okay, so there are many bots here, so you should spend some time looking at the existing bots and what they do. So if we look at the history of these crawlers, they can broadly be classified into first generation and second generation crawlers. The first generation crawlers were pretty simple. They ran on a single machine, and uh, they basically were interested in feeding a search engine. So like the www Wanderer, this was written in Perl, and it fed the index called the Wandex, which was quite popular at that time. So this contributed to the first search engine of the world as we know. This was in 1993. And then the mom spider is called the first polite crawler. Um, and then we also have Rupsy Spider, Web Crawler, Lycos Crawler, InfoSeek. So these were all search engines that showed up in the late 90s. And finally, we had the Google's crawler in 1998. From what we know in the published literature, this was implemented with Python. Had asynchronous IO, about 300 downloads in parallel, and it could fetch 100 pages per second. The second generation crawlers differ from the first generation crawlers basically on scalability. Mercator, for instance, could fetch 891 million pages in a crawl spread over 17 days. This is a 2001 crawler, and it's been a very popular one in the academic community. We also have Polyglot, which introduced this idea of URL frontier, which we will see shortly. We also had IBM Web Fountain, which was a multi-threaded process, and these processes were called ants, and the ants were crawling and fetching the pages. They also introduced the idea of near duplicate detection to reject web pages which were very similar. And they had several other interesting ideas like central controller for scheduling the tasks to ants. They used C++ and MPI, and used about 48 machines to crawl. And then we had a series of scalable crawlers, the UBI crawler, IRL bot, and so on. And we also had a few interesting open source crawlers. So now you could use Hitrich and Nutch. These are very active projects, Hitrix and Nutch, using which you could write a crawler yourself. So how does a crawler work? A basic crawl algorithm looks like this. So we start with the seed URLs, let's say about 10 to 100 web pages known a priori to be of good quality. And from those, so we go ahead and fetch the content of these seed URLs. So that's our downloaded web pages. And from those web pages, we extract links that show up. And so the extracted links um, are then followed and downloaded further. So this iteration continues. Um, and as we iterate more and more, we have more and more pages and more links, and again more and more pages, and so on. So this is how a basic crawl algorithm would work, but you might have noticed already that a crawler can't be as simple as this. So while doing these steps, they have to answer these requirements. The first one of them being scale. So we want to do this really quick because we have several billion documents on the web to go and download, and we cannot afford to download at, let's say, 10 documents per hour kind of pace. We are doing much faster than that. Okay. Can I get high value content quickly? So now that the coverage is an issue and I want to finish a crawl as early as possible, the question is always, can I get the high valued content, the most relevant, most important content first and quickly? And there's always a trade-off between coverage and freshness, as I just told you. Ideally, we would like to crawl every day and keep everything fresh, but that's just infeasible given the size of the web. So if I cannot guarantee freshness, let's say for a week, then at least can I, what? How can I improve my coverage? Or at the expense of coverage, how can I improve my freshness? So this is always a debate that's going on in the crawler world. Ideally, we would want both coverage and freshness. Okay. While doing all these things, we also want to be fair and polite to the website. Um, we don't want to bombard, do a DOS kind of an attack on a website and bring the website down. And we also don't want to generate extraordinary traffic to the website. Many of the website owners pay to host their content, and their bandwidth is pretty limited. So how to be fair to a website? So if a page has not changed, then we don't want to go and fetch that page. If we have hit one page just now, then we want to wait before we go ahead and hit the page once again to fetch the content. So these things refer to politeness while crawling. And you have to take this seriously if you're developing your own crawler. So let's say you want to go ahead and scrape the Google's search results. Okay. um, First of all, if you just go and programmatically hit Google with a query and start collecting the results, very soon Google will figure out that there is an extraordinary traffic coming from some place, and they'll simply block your URL, and after which you won't be able to access the site at all. So you don't want to get blocked. So that's another reason why you want to be fair to search engines. So usually the web hosts publish some fairness constraints, and you are uh, expected to follow that, honor that. Um, Finally, we also need to be aware of adversaries. Who are these adversaries on the web? So there are many fake websites which want to misdirect the traffic to their website. So let's say if someone expects that, okay, instead of typing ICICI Bank, a user might just type ICICI Bank, leaving out the middle I. And let's say if he wants to create a domain and take the traffic there and do something like that. Or let's say if someone searches for ICICI Bank, they want some wrong or fake website to show up in the search engine's results. Then they could do n number of things, which some of which we might discuss later in the course. So we have such fake websites, and we don't want to go to those fake websites. So the search engine's job is also to figure out which is an authentic website and ensure that the real ones are indexed and not the fake ones. And there is another very interesting thing called crawler traps, or spider traps. What are these? It's possible that once a crawler comes to my website, I never let the crawler get out of my website. How? So on a page which a crawler reaches, I'll put a URL dynamically which says, let's say, vvtage.co.in with a parameter question mark a equals 1. Now, if this is a new URL and the search engine doesn't know that this is same as vvtage.co.in, it will now add this URL to its extracted links, and it will go ahead and try to fetch vvtage.co.in question mark a equals 1. Now, when it goes to a equals 1, let's say I dynamically generate another page where I put another link which says a equals 2. Now the crawler tries to fetch a equals 2, and I can keep doing this infinitely long, and the crawler is stuck and busy in my website itself. So this is called a crawler trap. You could also extend the folder structures, like let's say vvtage.co.in slash foo slash bar slash foo slash bar slash foo slash bar. You can keep doing this and keep misdirecting the crawler over and over again, which is not generating any useful page for the crawler, but just that the crawler is trapped within your website. So you have to avoid all these kind of stuff, and these are the challenges which make implementation of a crawler really difficult. Okay, let's discuss about the scale. How do we improve the scale of a website? One way to improve the scale of a crawler, I should say rather, sorry. So how to improve the scale? There are a few things we could do. One key idea here is caching. So whenever we have a URL to be fetched, the first step that is involved is to do a DNS, a domain name server lookup. So if you don't know what DNS is, every URL has to be resolved to an IP address, and then we connect to that IP address over a specific port, and then issue a head or a GET request, and then go ahead and fetch the page that way. So the first step of resolving this name to IP address is a pretty expensive step. So it requires a lookup on a DNS, domain name server, which are a set of non-centralized servers which contain a map of IP address to names. And since this lookup is expensive, we would like to cache these IP address to names, so that next time when we crawl, we don't have to go ahead and look up. And, or even within a site, if you are crawling 10 different pages, for every page, for every URL, we don't have to do an IP address lookup. It's going to be the same, most likely. So we want to fetch the IP addresses and store them. So that helps in improving the speed of crawling. We also want to cache the robots.txt files, at least for a specific time range, and maybe it's worth refreshing the robots.txt after, let's say, a few months or a few weeks. And we want to avoid fetching duplicate pages. Now, understanding duplicate pages and near duplicate pages is a challenge. There are some nice algorithms to detect near duplicate pages. um, and also the same URL, if let's say I go fetch a website and extract the URLs from that website, and if one of those URLs is something which I have already fetched, then I should not fetch that URL again. So it's worth remembering the fetched URLs. And of course, we want to prioritize the URLs that we would fetch. So let's say we have extracted some 1,000 links, then we want to go and get fetch these links in an order of let's say freshness. So we want to fetch the fast changing pages first, maybe, or the more important pages first, maybe. So we need to have a strategy here to prioritize which URLs we would fetch. Here is a simple scalable crawl architecture. So let's say we have the web from which we are interested in fetching the pages. So as I told you, the first step in fetching is to ask the DNS. So give the DNS server the URL, and it will give you back an IP address. And once you have the IP address, you can go ahead and connect directly to the server and grab the page. So that's the fetch part. And we also have the parse part, after which after this, where you go take the fetched content and look for links, right? So the URLs within the page, and you are also interested in knowing whether this is a duplicate page which you have already seen, and so on. So that's another check that you want to do. And then we have a URL filter. So now we have extracted lots of URLs, and we want to ask if some of these URLs are not allowed by our robots, so we don't want them to be fetched, in which case we just drop those URLs. And if the robots.txt file allows us to go ahead and download them, we take the URL to the next step. Now, in the next step, we want to ensure that these are not duplicate URLs which are already fetched or which are already in our queue. So that's, once we have done that check, finally we put all our URLs to be fetched into what we call as the URL frontier. So think of this as a queue, a priority queue, which has lots and lots of URLs. Whenever we go fetch, we look for URLs in the content and we add them here after all the filterings. And this is a priority queue because we want to ensure that as we add URLs to this URL frontier, the one at the top is the one which has higher priority. So how would this work? So let's take a look. So we want so we have a queue of URLs per website. We went fetched a website and we got some documents, and then we collected URLs, and when we iterated like this, we got several URLs. and we could group these URLs as URLs per website. Yeah. So once you have such a queue of URLs per website, you could dequeue one URL, download that page, and extract the URLs from there and add them to the queue and iterate. So now we have, if we keep doing this, we keep getting queues of URLs. This helps us in distribution also. Now the question is, how would you know that a, a URL has already been served? Yeah, and this, you don't want to go and look at all the URLs that you have served so far. That would be very expensive. Is there a faster way? That's the question, and there seems to be a faster way. You could use a Bloom filter for this. So what is a Bloom filter? Let me switch back to a Bloom filter example. Okay, Bloom filter is a, so this is a very nice demo of Bloom filter on GitHub. Um, so let me explain the Bloom filter data structure. Bloom filter data structure is simply a bit vector. Um, So it's simply a bit vector where at a specific index position I can put a one, to say, to remember something. So let's say I get a string. I simply hash the string to some binary structure, and I keep putting ones, wherever that binary string takes me to. So if I get a series of string and I keep adding the hashed binary to this data structure, the idea is that if I get a new string, if I want to test whether this particular string exists in my Bloom filter, all I have to do is hash it and see whether the corresponding bits are set or not. So if one of the bits are not set, then clearly says that this has not been seen so far. This string has not been seen so far. If all the bits are set, then we don't know. We cannot claim that this string has already been seen. We can only say that this might have been seen before. So in which case we have to go and do a proper search, a proper linear search. Or if you have an ordered list of strings, we could do a binary search to make things a little faster. So let's say I initially have an empty bit vector, and let me add a site, let's say CMI. Okay, so I use some hashing algorithm such that CMI sets the 10th bit and the 13th bit. So if I keep adding CMI, it will keep setting the 10th and 13th bit. So there's no harm done here on repetitive adding. So let's say let's now add a IIT. So IIT adds few more bits. It might have added the 10th or 13th bit as well, but clearly it has added 7th and 14th bits here. And let's say I add India. Okay, few more bits are getting added. So this is what has happened. Now this is the state of my Bloom filter. Now let's say I want to ask if CMI is in my scene list. The moment I say CMI, it goes and hashes and checks that the CMI bits are indeed 1. So it says that maybe it's possible that I have seen this. Yeah. So that's the whole idea here. If let's say I use a unseen word, let's say America. Okay, so in if I do America, you see that it gives a wrong answer. It says I might have seen America, although I have not added America before, and that's because America again hashes to the same bits which one of these uh, words added, or a set of them added. So let's try some other word. Let's say Sri City. Now it clearly says no, Sri City has not been added, because when I hash Sri City, at least there is one bit which is unset at the moment, would be set if Sri City would have been added. So let's try Sri City. At least one new bit should be set. But before we do Sri City, let's do America and confirm that no new bits are set. Yeah, see, it again sets this same bit, so there is nothing new that is getting set for America. but if I try Sri City, you see a new bit getting added. So this is the idea behind Bloom filter. So now if you try Sri City, it should say that maybe yes, I have seen this. Okay, so this is the idea behind uh, Bloom filter, and we can take this ahead to implement the feature of whether we have seen a URL before. So this is really fast, much faster than doing a linear search. Let me switch back to my slides. Can same pages have multiple URLs? Think about it. And yes, sure they do. For example, vvtage.co.in, which is my website, can also be reached through www.vvtage.co.in. So these are aliases for my website. So they can have multiple URLs. You can set up as many aliases as you want. uh, slash index.html also takes to the same page because that's the default file. You don't have to specify it, so that's again another case. And I can have www.vvtage.co.in slash index.html. So all these four URLs are essentially the same thing, right? And if I put any parameters and add them, it's again going to give the same page. That's because I know it's my page. Yeah. So it's possible that multiple URLs may point to the same page. So there is a need for crawlers to canonicalize these URLs. um, One way to do that is when I set up these kind of index.htmls, I could just create a header part of the HTML, and in that I could tell that hey look, the canonical URL of this page is this. So which tells the search engine that the highest priority should be given to go ahead and download the canonical URL and not the other forms of the URL. And it's worth remembering the canonical URL for a URL, so next time you don't have to do that check, and you can, whenever you get any of these URLs, you just ensure the canonical URL is downloaded or not. Now let's focus our attention to a brilliant idea called frontier expansion. So recall that we discussed URL frontier in this context where we add um, the unseen URLs which are supposed to be fetched into a priority queue called a URL frontier. Okay, now that we have, so it starts with a seed URL and then we go ahead and fetch the documents. And from the documents, we get more links and we fetch more documents. And as we do this, the queue or the URL frontier grows, right? This is what we call as a frontier expansion. uh, so here is a very interesting question. Should we do a breadth first scroll over the web, or should we do a depth first scroll over the web? What do you think? It's a good time to pause the video for a minute and think. Okay. The problem with a depth first scroll is that our spider or our crawler can get trapped within a website. I might never have a chance to go and fetch another website at all. Right. So that's one risk that we take by doing a depth first scroll. We could do a breadth first scroll, but there are so many websites out there that it might take a really long time to get back to the next pages on the same website. Yeah. So this is the trade-off between the breadth first and depth first scroll. We usually do a breadth first scroll, so we ensure that we have a broad index. And doing a breadth first scroll also uh, is enabled in a way because we have a per website queue of URLs. Okay, the next question is how frequently to crawl. Crawling the whole web every minute is technically not feasible. So what is a good crawl frequency? So to understand this, we need to model these pages a bit. So let's introduce some metrics and terminology here. So let's assume I have a page P1 refers. So now in this case, I have a crawl, and a crawl refers to a set of pages pi collected from one crawl over the web. Now, let's say we have a page pi, and let's say in that there is one page p1 for now. Let's keep things simple. And this page p1 is fresh if it hasn't changed after we crawl, and is stale if it changed after we crawl. So now we define freshness as simply the number of fresh pages in our crawl over the total number of crawled pages, or the size of my crawl. Now, what is, I mean, is this a good metric to say how good our crawl is, and is this I mean, do we see anything wrong with this metric? Again, pause the video for a minute and think. Well, the problem here is fast changing websites bring freshness of our crawl down. Um, so the problem here is that the fast changing websites bring freshness of our crawl down, right? So if this was a metric, then a way to improve your crawl's effectiveness is simply don't crawl at all, right? Either don't crawl at all, or don't crawl only static pages. But that doesn't seem to be the right thing to do. So can we do any better? Can we come up with a better metric here? So we find age is a much better metric. So let's say again, let's define age. Let's say there's a page P1, and P1 has age 0 at the time it is changed, and then it grows, the age grows until the page is crawled again. Okay, so this is what happens. The page remains at 0 until it is updated, and when the page gets updated, then as the clock ticks, the age grows along with the clock, and at some point of time we go ahead and crawl it, and the moment we crawl it, its age resets to 0. And then if there is no update to that page at all, then the age stays at 0, and whenever there is an update before I do my next crawl, the age again starts growing with time, right? And at some point of time I again go ahead and crawl it, where its age comes back to 0. So this is how I define age of a page. Suppose P1 changes lambda times per day. Okay, so let's just define a parameter lambda, which gives the change frequency. Then the expected age of P1 after t days from the last scroll. Okay, so t days from the last scroll is simply given by integral over 0 to t probability that the page changed at the time x, and t minus times t minus x ds. Here you can notice that t minus x is the age of the page, uh, because it's t days from the last scroll, right? So that's why we have t minus x over here. So the expected value is simply this, and it's we can see that the pages change independently and at random, so we could fit a Poisson distribution to this, and so the expected age can be estimated simply using the lambda, which is our change frequency, right? So the expected age simply becomes integral 0 over t lambda e power minus lambda x times t minus x dx. So we now have some way to know whether a page has become stale or not, or a crawl has become stale or not, and when to go ahead and do another crawl. Usually we do this when we know that okay, the expected age is this much. Okay, a word on crawler traps. There are plenty of crawler traps over there on the web, and sidestepping them is pretty important. So here is an example. As I had told you, it can be set up by spammers like slash foo slash bar slash foo. They keep on redirecting you inside their inside their website, and this if you look at some of the archive contents, you see that there are so many millions of URLs being queued. Now, in this case, archive.org may not be a spam website, but these are usually indications that there could be. For example, if you have million URLs in a Wikipedia website, then you know that okay, it's not a spam website. But for a small website, if there are million URLs getting queued, then you should be cautioned. There have been several ideas to counter this. One idea is was published, which was called Beast, the budget enforcement with anti-spam tactics. So they go ahead and associate a cost with fetching each URL for a website, and then um, ensure that they don't spend too much time into one website, into one URL. Um, we also have this batch versus incremental crawling. We don't have to every time, let's say a crawl takes 17 days. We don't have to like spend 17 days crawl and then again after 17th day start a fresh new crawl for 17 days. So that is not the only way that we could crawl. A better way could be incremental crawling. What do we mean by incremental crawling is you first do a full crawl and get a snapshot, and in every incremental iteration you just update your past crawl. You either add some pages or you update some pages, or if some pages are no more there, then you just remove those pages. Now this could be a little more cost effective than do a full crawl. Now, this incremental crawling is easy for static web pages, because you know that okay, these static web pages either go away or get modified or don't change. So in which case my idea of updating the existing crawl works. But what if we have too many dynamic web pages which are changing every day? So which means pretty much you have to replace all the pages. So if your crawl is made up of all dynamic pages, then all the pages are going to get updated anyway, whereby it essentially becomes a batch crawl. Batch crawls are easier to implement. It's straightforward, but incremental crawling, you have to be careful on how to do that. Okay, so batch crawl works well with dynamic web pages for the reason I just mentioned. We usually mix them both, or uh, we do ensure that we know which pages are static and which pages are dynamic. So our incremental crawls don't spend too much time on the static web pages. Thereby, we gain something. For those who are interested more on incremental crawling, there's a good write-up by Kevin McCurley on incremental crawling, which I suggest you go and read. Okay, given the scale of the crawling, we no more use a single machine to do the crawl. Although with a single machine you could crawl a large number of websites, but still, if you're talking at web scale, we would like to go distributed. Now, the question is, can we use cloud computing techniques to distribute this crawling task? So most modern search engines use several thousand computers to crawl the webs. But then the more you get distributed, you have new challenges now. How do you know that the different systems are not going and fetching the same content? In which case, we are not being polite to the website, right? We are unnecessarily crawling and generating traffic for that website. So how can we avoid this? So that's the question, and we don't want to do DNS lookups from so many different machines for the same URL. So these are things which we need to worry about when we are implementing a distributed crawling. So there are quite a few solutions again from the research community. So one way to do that is distribute per site load to each node, and let them take care of downloading some sites. So if you have some, let's say, millions of sites to crawl, then we keep adding all the URLs belonging to specific sites to specific nodes. So each node, let's say, has 100 sites to crawl, and all the URLs of these 100 sites belong to a node. So this is one idea, but this might not be the most effective idea, because we might not achieve good load balancing in this case. So we need to ensure that not some nodes are overly busy and some nodes are idle. Uh, so another idea is to use a central URL frontier. Caches and queues, so all these things are central, but just the fetching task is distributed to the mappers if you are using a Hadoop kind of infrastructure. So that's another idea which simplifies the same thought process. More on this from Cho and Garcia Molina in their paper Parallel Crawlers, which is worth reading. So let me round up what we have discussed so far. The way a basic crawler works is it starts with some seed URLs, which is well known beforehand that these are quality web pages. And from there, we download the web pages, gather more URLs, and then go ahead and grab more pages and so on. So we keep iterating this again and again till we think we have gathered the entire web, or we have no more links to fetch. Can I get high value content quickly? How do I scale this? So these are important questions. For scale, we saw distributed crawling, and we also saw how to use the URL frontier idea to ensure that we have a priority queue and we are doing things in a more effective way. We also want to eliminate duplicate URLs and so on. So for high value content, again, we looked at sitemaps to check the priority as given by the site owner, and there are a few other techniques, as in we try to eliminate the fake pages or push them down. If we can detect them, if we can detect near duplicates, and we also look for frequently changing pages, and ensure that they are downloaded more often, whereas static pages are not downloaded that often, and so on. Coverage versus freshness is also a criteria. We know we cannot go ahead and fetch the content every day or every minute, but at the same time, we care for the freshness of our crawl. So there is a trade-off here, and we want to ensure that we balance these better. How to be fair to a website is a very important criteria. We don't want to bring the website down by loading them with requests for all the web pages on their machine. So we honor their uh, fairness requirements. And of course, while implementing a crawler, we have to be careful that we don't get into a crawler trap, or we don't fetch fake websites, and we don't end up promoting fake websites as a search engine. So these make crawler a very interesting tool to implement. Here is a example of what a single machine can do. I pulled it up from a blog on dzone.com. So with a hardware such as Xeon E5, which is a 4-core 3.7 gigahertz machine with a 64 GB RAM and a Ubuntu server, Nutch is a tool which Nutch is a crawler which we will see shortly. And there's another called a storm crawler. So they have run this on this hardware, and they could fetch about 11 million URLs in 32 hours. Similarly, storm crawler could do even better with 38 million URLs in 66 hours. So this is what you could do with a single machine and a modern crawler today. And setting up these crawlers are just minutes work, not even days. It's that easy. So most of the things that we have seen so far has been taken care of and implemented in Nutch. So let's take a quick look at Nutch. It's a highly extensible, highly scalable web crawler. We now have Nutch 2.x as well, but Nutch 1.x itself enabled fine-grained configuration relying on Apache Hadoop data structures, which are great for batch processing. Using a modern crawler is pretty easy. I take the example of Nutch here. You could get a more detailed tutorial at this website mentioned in the footnote. Um, but crawling these days is pretty simple and very straightforward. So you start by naming your agent. So there is a configuration file where you could go ahead and name your agent, let's say CMI crawler, and you have a seeds file. So you create any file and put few seed URLs there, let's say cmi.com, yahoofinance.com, or you put few sites which you think is authentic. And after that is done, we are ready to start the crawl process. We initialize the Nutch crawl DB. So Nutch uses a crawl database, a database called crawl DB, where it goes ahead, it fetches, where it stores the fetched web pages. So how do we do this? So we simply do Nutch inject URLs. So this will go ahead and use the seed URLs, fetch the content, extract the URLs from there, and inject it into another DB called the link DB. Now we are ready to go ahead and iterate. And to iterate, we say generate. We just use Nutch generate, and we can limit this to 100 top quality URLs, or just say Nutch generate, which will go ahead and iterate. Now, fetch the, so once you have collected, let's say 100 more URLs as given here, then now you can go ahead and fetch the content for those 100 URLs. So we do that using Nutch fetch hyphen all. So all those URLs are fetched now. And once we have fetched, we are interested in parsing them. We do Nutch parse all. So whatever we have in our crawl DB is parsed. And after this is done, we just update the DB with more links if we have any, and we can index the content that we have in Solar directly. Now these are all simple calls to some batch scripts like Nutch update db hyphen all, or which would do the update part of the DB, or we could simply do Nutch Solar index, give the URL of your Solar installation and say hyphen all these data that you have crawled will get into Solar and it's ready for querying. So it's as simple as this. So we just started with by creating a simple agent and creating some seed URLs, and then a bunch of commands to set up Nutch, and that's about it. Of course, I have dropped few steps over here. You could do deduplication of the URLs as we just saw in the overall architecture. So there is a library given to you for that. You could also do link inversion to know that which links are associated with which pages, instead of that being the other way around, that pages be carrying links. I have dropped them here for simplicity, but if you should look at this tutorial which explains these things in detail. I leave you with these references for learning more about Nutch. So there's a YouTube video from the Berlin Buzzwords 2010 talk by Andres. There is a Nutch tutorial website which lists all the commands in a nice way. And of course, this paper is a good read, Web Crawling by Christopher Alston and Mark Nayok, in the Foundations and Trends of Information Retrieval. With that, I stop here. Look forward to see you with another interesting topic in information retrieval soon. Thank you.